Hey everyone, it's Cal from Wise Guys Tutoring. Today I'm going to be solving the EmSAT Math specimen questions that are online for 2022. It's actually pretty great, so it's all online and they give you a score once you're done, and every time you register again, you get new questions, or at least some of them are different. So it's really good practice. I recommend you do it. I'll put the link in the description. I'll also take the chance to remind you guys that I offer private and group lessons for the EmSAT Math, so get in touch with me through Instagram at WiseGuysUAE or email me at info@wiseguysUAE.com, and yeah, we'll talk about it. So without further ado, let's get started. Question 1 says, a car passes a gas station on a highway traveling at a constant rate of 45 kilometers per hour. 1 hour later, a second car passes the same gas station traveling in the same direction at 70 kilometers per hour. How much time in hours after the second car passes the gas station will it overtake the first car? So you got to think about these questions. This kind of, it's almost like a physics problem, but let's picture the gas station here. Okay, we'll put a little gas pump, why not? And let's picture there's car A. It passes this gas station here, car A, and it's going at 45 kilometers per hour. Okay, that's the speed that it's going right now. And then they say an hour later. So let's do the same scenario. Let's say the same gas station is here, still got that little pump. Doesn't really look that good. There you go. And now there's a car B which is passing the gas station, and car B is going a little bit faster, right? It's going at 70 kilometers per hour. But you have to remember that this car A has been driving for 1 hour, right? So car A is probably somewhere ahead here if it's been driving for an hour, and it's still going at 45 kilometers per hour. Okay, this is the idea that we're working with. Now you can tell that the red car, car B, is going faster, right? And it's going in the same direction. So necessarily this car, this red car, is going to overtake the blue car sooner or later. Okay, it's just a matter of when and how far down the line. So first we got to start with a couple of basics. When we're talking about speed, distance, and time, this is the relationship. You may notice that we put that it's kilometers per hour, or it could be miles per hour. So that's always kilometers, like a distance, per hour. So distance over time. This is a very, very, basic foundational equation. Let's call it speed. V equals d over t. Okay, usually we use v for speed in physics, like velocity. So now the distance part. So when we're talking about the distance that you've traveled, you can use a little bit of algebra here, and you can multiply both sides by time, right? We know about this. If you're not sure, you can check out our algebra videos that we've done. We've done several on that. So you get velocity times time. So speed times time equals distance, right? So distance will equal the speed that you're traveling times the time that you've been traveling. But also I'm going to add a little something, is the initial distance. So the initial distance represents how far you're already traveled, right? Like in the case of car A, it's already some kind of distance ahead of car B. It's already some kind of distance ahead of that gas station because it's been traveling for 1 hour, right? So if you break down this equation, what it is this part tells you if you're going at a certain constant speed for a certain time, you will cover some distance, plus whatever distance you had covered already. That's going to be your total distance, let's say from the gas station. So if we do this, when you say you want car B, or the second car, to overtake car A, what that means is that they're going to be at the same distance at the same time. That means we're going to have to equate the distance of car A with the distance or position of car B. We're going to say car A was traveling at 45 kilometers per hour for some amount of time. And also we need this initial distance it had traveled. So if this car was traveling at 45 kilometers per hour for 1 hour before B got there, right? We're going to use this equation here. So the distance it had traveled was 45 kilometers per hour times 1 hour. So it had traveled 45 kilometers. So it is already 45 kilometers ahead of car B. So I'm going to add that here, right? That's the initial distance that we talked about. So this is for car A. Now let's do car B. Car B is here. It's traveling at 70 kilometers per hour for some amount of time to overtake. and its initial distance is 0, right? We're considering that this is the beginning, the 0 line. So I don't have to add anything. You could put plus 0, but as you know, we don't really do that. So now it's just a matter of algebra for us to solve for t, right? So we got the distance that car A is at, the position or the distance that it's at, and we have car B. Now, at what time are these two going to be equal? So now all I have to do is solve for t. I'll remove 45t from both sides. I'm going to end up with 45 equals 25t. To get t all alone, I divide both sides by 25. And now I'll get that t, put that in your calculator, you get that t equals 1.8 hours. And that'll be the answer, 1.8 hours. It says do not round your answer, so 1.8. There you go. Let's do number 2. So this one's a fairly simple, straightforward question. It says identify the expression that is equivalent to the expression shown below. And there's some parentheses, so let's talk about what that means. When we have the first two terms over here, okay, they're in a bracket, that's fine. When we come to the second one, there's a bit of a difference, because when these two are in a bracket and it's being subtracted, there's something that happens. When you don't see the number here, it's as if there is, you know, a 1, an invisible 1, minus one of these, right? And we know that when we have a constant in front of the bracket like that, what's meant to happen is we're distributing this guy. That's what parentheses do. The parentheses here means whatever happens to one of them happens to both. Okay, whatever is happening, if they're being multiplied, or if there's a power, for example, or if they're being divided, it happens to both. So if we're going to distribute this one, what happens is this. These guys are the same as they were. Minus 1 times 7x squared is minus 7x squared. And minus 1 times minus 6x cubed is positive 6x cubed. Okay? If you want the shortcut version, whenever you have a negative in front of a bracket, you can just straight up change the signs of everybody in that bracket. Okay, the positive 7x squared became negative, and the negative 6x cubed becomes positive. Why? Because this negative here is distributed to both. Okay, because of the bracket, this negative is distributed to both. It is not only applicable to the 7x squared. Okay, so now that we've done that, we can basically just do the grouping of like terms. So what I like to do is, you know, I have nice colors, but you guys can use shapes, or you can do one line, double underline, whatever it is. So the 3x to the 5 is on his own. I also have some 8x cubed here. We have 6x cubed. Now notice I like to always take the sign with it. Okay, I'll remind you that the sign belongs to the guy after. For example, over here, this negative belongs to the negative 7x squared. It does not belong, you know, to the equation or shared. It belongs to the 7x squared. Okay, so now that I've done that, I can group them. So 3x to the 5. Remember, when we are collecting like terms, you have to make sure it's the exact same letter and the exact same exponent. Otherwise, they do not mingle. Okay, so next I'll do the x cubed. I have 8 over here and I have 6 over here, so that gives me 14x cubed minus 7x squared. Okay, he's also alone. So which one of these expressions is the same as mine? It is third one, C, or whatever you want to call it. And that's how you get it. So let's move on to question number 3. Okay, question 3 says a random number generator is used 2,400 times to generate a number from 1 to 6. Identify the statement that best predicts how many times the number 3 will appear out of the 2,400 generated numbers. So this is a question about relative frequency. Relative frequency, which is very closely related to probability, experimental probability. Basically, if you have a random number generator and there are numbers from 1 to 6, what that means is that they each have an equally likely chance of appearing, right? You have 1, 2, 3, 4, 5, or 6, kind of like rolling a die, right? So the probabilities of each one is 1 out of 6, right? They each have an equal chance of being picked or generated in this case, and the total probability must always equal to 1. Like when I add them up, they always equal to 1. That's how probability works, right? There are no other choices. There's only 1, 2, 3, 4, 5, or 6. So the probability that I'm getting one of these numbers is 100%. It's 1. It's sure. It's going to be 1, 2, 3, 4, 5, or 6. So if it's a random number generator, then I'm assuming it's a fair number generator. So that means each one has an equal likely probability of appearing. That being said, if I am doing this random number generation 2,400 times, okay, what I would expect is that 1/6 of those times, I'm going to get the number 3. So if they're asking me for the probability or how many expected 3s I'm going to get, well, I expect to get 1/6 of those 3s. That means I expect to get 2,400 times 1/6. So I expect to get 400. And you'll notice that I'm like a broken record saying I expect to get 400. Because here's the deal. Let's say you have a coin, okay? If you have a coin, there are two choices, right? You flip the coin and you get either heads or tails. And let's say it's a fair coin, so there's a 50-50 chance of getting heads or tails. Now, let's say I'm an alien and I come from outer space and I tell you, okay, flip the coin, let me see. And you flip it 2 times. It's very possible that you get heads, right? It's very possible because you flipped it twice. It's not a supernatural thing to get heads. But if I'm an alien, you know what I'm going to say? I'm going to go to my planet. I'm going to tell everybody, hey guys, on Earth, when you flip a coin, you get heads all the time. It's always heads. And obviously that's not true. And the reason is because 2 times is just not enough. It's too little. The number of trials is too little, right? But I guarantee you, if I come and I tell you, okay, flip the coin 10,000 times. If you flip it 10,000 times, more than likely you will get almost 500 heads and almost 500 tails. Sorry, 5,000 rather. It's going to be really, really close. And this is called the law of large numbers when we're talking about statistics. So the law of large numbers means that the bigger the number of trials that you do, the closer your experimental, your actual mean will be to the theoretical mean that you calculated. So that's why in this case, when you're doing 2,400, if you want to know what's the expected value, it's 2,400 times the probability. That's the equation that you should know, okay? It'll be the number of trials times the probability. That will give you the expected value, okay? That's what you should remember from this. And like I said, the law of large number means the higher the number, the closer your actual values will be to the theoretical expected value. And why I say expected is because you can spin it 10,000 times. It's possible to get 10,000 heads and 0 tails. But is it likely? Absolutely not. But it's possible, okay? When we talk about probability, we're talking about likelihood. So you cannot say it will come exactly 400 times. That's just not true, okay? You have to say it will appear close to 400 times, but most likely not exactly 400 times, because that's how life works. Nothing's going to come exactly as the probability described. I can tell you it's going to rain 80% of the days, right? But if you have 10 days, is it going to rain exactly 8 out of 10? No. It might rain 0 and it might rain 10, but more than likely it'll rain, 7, 8, 9 days. Okay, so when it comes to probability, remember, it's not exact. Okay, that's why these exact ones don't work. And 480 is not correct. It's because you have to multiply 2,400, the number of trials, by the probability, which is 1/6. There you go. Let's move on to number 4. All right, so number 4 is about limits. It says, from the table below, the limit as x approaches 3 of f of x equals, and then they give us a table. So let's talk about limits. I'll give you an introduction because we're not about to go into a whole calculus class, but here's the basic gist of it. When you say limit as x approaches 3, let's imagine we have a function, not this one, just a different function. Let's say we have x squared minus 9 over x minus 3. Now, one way to tell what's going to happen when x is equal to 3, right, is just to directly substitute 3 in here. And what would that give us? Let's see. If I put 3 in here, you get 3 squared minus 9 over 3 minus 3, which is 0 over 0. And this is undefined, right? You can't divide by 0. It doesn't mean anything, 0 over 0. So what we're going to try to do is put values of 3 close to 3, right? Because 3 doesn't work. But let's see what happens when we get really close to 3 in a step-by-step way. So let's say I put, let's call this f of x, right? So let's say I put f of 3.1, right? I put this in my calculator and I do 3.1 squared minus 9 over 3.1 minus 3. What does that give you? It gives you 6.1. Okay, let's get a little bit closer. So instead of 3.1, let's get closer. Let's make it 3.01. So now I'm really close to 3. I'm closer, right? It's 3.01. Here you go, minus 9, 3.01, minus 3, beep, boop, beep. You end up with 6.01. And if I want to get even closer, let's overdo it. Let's do 3.0001. So it's like, it's almost 3. It's so close to 3. It's crazy, right? You put this in your calculator and you're going to get 0001 minus 3. You get 6.0001. So obviously, the closer that I'm getting to 3, the closer I am getting to 6. And that's what the limit means. It means as x is getting closer and closer and closer to 3, this ends up getting closer and closer and closer to 6. And that's why the limit here, the limit as x squared minus 9 over x minus 3, as x approaches 3, the limit is 6. Okay? And you can tell that's what's happening with the table. So for now, we can answer the question, right? So as x is approaching 3, you can tell as x is getting closer and closer and closer to 3, the value of f of x is getting closer and closer and closer and closer to 10. So the answer here will be 10. Okay, but as usual, I don't want to just give you the answer. I want to give you a little bit more about limits. So give me a second. So check out this graph here. This graph is for a function. Let's call it f of x. And the function is defined as, you can tell, it's just a parabola, except for at x equals 2. When x is equal to 2, this function is 1, which is what this point is right here. When x is 2, f of x or y is 1. Otherwise, it acts like a parabola, like a good old-fashioned x squared parabola. So if I was going to ask you, what is f of 2, right? So when x is equal to, well, that just equals to 1, right? There's a little hole here. When x is 2, it's actually equal to 1. But now what if I said, what is the limit as x is approaching 2 of this function, f of x? So let's do the same exercise that we did like for this table. Okay, let's try f of 1.9. Right? So it's not 2, but you know, it's getting close to 2. So 1.9. If I put this in my calculator, 1.9 squared, what I'm going to get is 3.61. Let's get a little bit closer. Let's say 1.99. That means 1.99 squared. That gives me 3.9601. And let's overdo it. Let's get super close. Like let's put 5 9s or something like that, right? So you get 1.99999 squared. Well, now you're at 3.99996. So I think you can tell that it's getting closer and closer to 4. And we don't have to go just under the 2. We can approach it from the right side here. So we can go just a little bit, a hair above 2, like let's say 2.0001. So if I take this and I square it, put that in your calculator, you'll get 4.00004, right? So I can safely say that the limit as x approaches to of this function is 4. It's equal to 4, right? So what we're talking about is this one over here. That's the orange one. As I'm approaching from the bottom, it's trying to get to 4. It's getting closer and closer to 4. So that's what the limits do, okay? It's trying to define an undefined value, whether that's a whole or whether you get an undefined, 0 over 0, or sometimes it'll be infinity over infinity. It's helping us define what's going on in the function when it's undefined. Okay, so in conclusion, the answer is 10. Question 5 is also about limits. It says find the limit as x approaches 10 of log a of 1. So I'm assuming this is a typo, and this down here shouldn't be a. Maybe that's supposed to be x, like log of x. Before that, let me give you a quick background on logarithms. So log of something, a, let's call it, of b, is kind of another way. It's the inverse of exponential functions. So what this means, if I were to convert it, is this. A is the base, and whatever you have here, let's say this equals to c. What this means is a to the power of c equals b. So I was always taught it's like a seashell shape. Seashell shape. Say that 10 times fast, right? So it's a is the base to the power of c, and the answer is b. So it's kind of like a reverse of this. They are inverse of each other, in fact. Okay, that's how logarithms work. So I'll give you an example, a numerical example, hopefully easier to follow than my jargon. So let's say the base is 2 and I have 8 here, and I say, what does this equal? Well, what they're asking us is 2 to the power of something equals 8, right? So the answer here is 2 to the power of 3 equals 8. So the answer here is 3. Log base 2 of 8 is equal to 3. That's how logarithms work. So let's take our question, our function that says limit as x is approaching 10 log base x equal of 1. What does that equal? So we can try by direct substitution, right? We can put numbers that are getting closer and closer and closer to 10. Whatever it is, let's say we use 9.1 or 9.9 like we did earlier, of 1, right, equals something. Again, using this like seashell method, let's call this number c or something. That's the answer. So it would be 9.9 to the power of c equals 1. And then if I take another number, so I can write that for us here so we don't forget. So it's like 9.9 to the power of c equals 1. And then if I use a number even closer to 10, right, because we're approaching 10, so 9.99 of 1 equals c, then I do the same thing. And what this means is 9.99 squared equals 1. And then I can get even closer to 10, or I can even try 10 itself equals c. And this will mean that 10 to the power of c equals 1. I don't know why I put 2 here. So what is this value, right? What is this value? It's always 0, okay? Anything to the power of 0, anything at all to the power of 0 is always equal to 1. No matter what number you do to the power of 0 is always equal to 1, okay? So whatever it is, I'm always getting 1. Well, that must mean that c, this one here, the answer of my logarithm, my limit, it's got to be 0. That's the only one that would work. To be honest with you, this is a very strange question. I feel like there's a typo. But anyway, I took it as a chance to show you guys a little bit about logarithms, and again, a little bit about limits, you know, how we practice this. But yeah, anything to the power of 0 equals 1. That's the only way you're going to get 1 as x is approaching 10 for any value. So there you go. Those are the 5 questions. We did a little limits, which is pretty new, which is awesome. It's always cool to do new topics in case they come up in a test. If you guys have any questions, comments, suggestions, please leave them below. I'm always happy to interact with you guys. Again, if you need private lessons, just DM me on Instagram or send me an email. I'll put the information there. As usual, please like the video and subscribe to the channel. I'm going to make a lot more because now there's a ton of questions to do. So be on the lookout for new videos. All right. Thanks, guys.